We live in an age of digital certainty, where computers and sensors watch over everything, from our bank accounts to the traffic lights guiding our commute. We naturally assume our digital systems are precise, exact, and always aware. But beneath the surface of this reassuring digital certainty lies a surprising fragility, a quiet danger built into the very foundations of how computers understand the world. Consider the recent Heathrow power failure. A single transformer fire plunged Europe's busiest airport into chaos, stranding hundreds of thousands of passengers. But was this really just about a fire, or did something subtler amplify the crisis? When computers handle numbers like pi, the circle's magic ratio, or precise temperature curves, they do so approximately, not exactly. Imagine cutting a circle from cardboard. No matter how carefully you cut, your circle isn't mathematically perfect. In much the same way, digital systems store crucial values with slight rounding errors. These small differences might seem trivial, like pennies rounded away at the store, but they silently accumulate and feed into critical decisions. When a transformer heats up, sensors feed temperature data into control software. But if the software's model is off by even a tiny fraction of a degree, the system might mistakenly assume all is well. This happened at Heathrow, where delays caused by digital approximations meant warning signs emerged too late, causing transformers to fail catastrophically. Imagine an orchestra where each musician's timing drifts slightly, barely perceptible at first, but after a few bars, the harmony falls apart. Something similar can happen with grid frequency. Every generator on the power grid must stay perfectly synchronized, keeping the electrical frequency stable, usually exactly 60 Hz or 50 Hz. Digital systems measure and adjust this frequency using approximations. But each approximation, even by microseconds, can ripple outwards, magnifying over time. Consider a solar farm using digital controllers to match the grid's frequency. A tiny rounding error in frequency measurement might seem insignificant, but that minuscule error causes the solar farm to slowly drift out of sync. Neighboring power plants then try to correct for this drift, adjusting their own outputs. Suddenly, what started as a negligible approximation has grown into a dangerous instability, capable of blacking out entire cities, a domino effect initiated by digital rounding errors. Digital control systems, like the supervisory control and data acquisition, or SCADA, systems managing power grids, often rely on simplified, digital models of reality. These models are never exact. They're pixelated, like low-resolution pictures, but the digital grid believes these pixelated images to be real. Imagine a control system receiving slow or incomplete updates, much like a delayed video feed. Decisions made based on outdated or incomplete data create a feedback loop. The grid takes actions based on partial reality. These actions alter the system, and then the altered system is misinterpreted again. It's like navigating through fog while insisting you see perfectly. Such illusions famously contributed to major blackouts, including the 2003 Northeast blackout, when control systems, misled by inaccurate data, failed to prevent a cascading outage. Today, as grids grow more digital and more interconnected, the potential for these illusions grows more pronounced and more hazardous. At this point, one might wonder, why haven't engineers resolved this already? The challenge lies in visibility. Small numerical errors and approximations are practically invisible until something catastrophic happens. When grid operators and engineers see perfectly smooth curves and neat tables of numbers on screens, they assume stability. After all, the digital systems appear precise and orderly. Yet behind that reassuring screen is hidden complexity. Errors multiplying silently, system-wide harmonics drifting apart, digital illusions diverging quietly from physical reality. Often these hidden instabilities only become obvious once it's too late, when physical systems fail spectacularly, as in Heathrow or during citywide outages. Fortunately, this subtle danger isn't inevitable. Awareness of digital approximation pitfalls can lead to better design and safer grids. Engineers can build redundancy into the digital layer, not just physically, by cross-checking approximations and using multiple methods to measure and verify critical variables. Just as pilots trust multiple instruments rather than just one gauge, Grid operators must use layered systems to verify the truth behind their numbers. Ultimately, confronting the quiet danger within our digital grids means acknowledging that digital precision is an illusion. It means designing systems humble enough to question their own assumptions, rather than blindly trusting digital perfection. Heathrow's blackout, though costly and disruptive, offers us a crucial lesson, one we ignore at our peril.